for joining us for the IEEE Computer Society Standards webinar series, brought to you by the Standards Activities Board. With over 225 standards that transform the way we live, work, and communicate, the IEEE Computer Society sets the standard for design automation, simulation, testing technologies, Ethernet and Wi-Fi, quality assurance processes, systems architecture, DevOps, and more. Standards deliver best practice processes for developing market-ready interoperating systems, products, and services. You can have an impact by joining one of the over 200 IEEE Computer Society Standards working groups. Participating in one of the working groups grants you access to information that reduces risks, increases proficiency, and shapes the future of the industry. Help determine what's next in computing technology. Learn more about our standard working groups at computer.org/standards.
Hello everyone, and welcome to today's webinar from our Standards Activities Board webinar series, The Journey to 800 Gigabit and 1.6 Terabit Ethernet by John D'Ambrosia. My name is Scott Levine, and I'm the membership manager here at the IEEE Computer Society. I'll be your host and moderator this morning. Before we get started, I'd like to address some housekeeping items. This webinar is being recorded, and you will receive an email tomorrow which will include the copy of the slides and the recording. If possible, please reference the slide your question refers to, and John will answer as many questions as he can following the presentation. As mentioned, joining us today is John D'Ambrosia, a distinguished engineer at FutureWay Technologies, a subsidiary of Huawei. John is the chair of IEEE 802.3dj 400 gigabit and 800 gigabit per second task force, the IEEE 802.3dj 200 gigabit, 400 gigabit, 800 gigabit, and 1.6 terabit task force, and the 802.3CW 400 gigabit Ethernet over DWDM systems task force. John is also a member of the IEEE 802 LMSC Executive Committee, IEEE senior member. In addition to his multiple roles in 802, he was an advisor to the European Photonics Industry Consortium from 2019 to 2022. He was the chairman of the Ethernet Alliance from 2011 to 2019. His previous work experience includes Dell, Force 10 Networks, and Tyco Electronics. John, thank you for being here today, and the floor is yours to get us started.
Thank you very much, Scott. Can you hear me okay, just to confirm?
Yep, you sound great.
All right, thank you very much. Well, before we get started, I guess I have to get my geek on and wish everybody a happy May the Force Be With You Day. I think that is a global thing, so may the Force be with you. I'm not going to go over all my industry involvement. Scott just did a wonderful job on that, but I am going to point out that anything that I say today in accordance with the Standards Board bylaws is my own opinion, and I'm not presenting on behalf of IEEE. So we have a very lengthy session in front of us, so let's get started. Let's do a little brief introduction first. So some of you may not be aware that Ethernet is currently at 400 gigabit per second Ethernet rate. That is the maximum rate. There are a bunch of rates. I believe the last count was at 12, ranging anywhere from 10 megabit to 400 gigabit. Whenever we decide or are considering starting a new speed for the past couple speed turns, we've actually done what we call an Ethernet bandwidth assessment. So the last one that we did was in 2020, and it would be really great if that bandwidth data was just readily available and you could go out and just look at the numbers, but unfortunately it isn't. So rather than trying to just base it on pure bandwidth numbers, what we do is we actually look at this equation, which we have found to be very fundamental to the growth rates over the past three speeds. So three speed jumps. Basically, it's the number of users times the different access methods and rates times the services, and any one of these or all of these together combine to create a bandwidth explosion. The last one, as I said, was in 2020. If you want to find out more information, read the report that was written by the 802.3 community, or even watch a tutorial, please go to the links below. That information is all readily available for you. It does a wonderful job of going into a lot of details. I'm going to probably not get into that too much today, but I'm going to just kind of jump to the summary and conclusion of that work. This is essentially looking at our forecast that we did. So we went and we looked at everything really as far back as we could, going back to 2017. So mind you, this report that was gathered, information gatherings was really the year of 2019 and writing. And we normalized it all back to 2017, which was when we did the last speed jump. So we looked at a host of different application spaces. Virtual reality, IP video, mobile consumption of data, the mobile market, data center capacity was being shipped, content delivery networks, IP, peering, and we plotted what we could, and that really went out to 2022, and then we just had to assume a CAG, right? We assumed a constant CAG in that time frame to get a reasonable estimate of what the growth would look like. And what you really saw was that traffic normalized to what it was in 2017 would be growing anywhere from 2-3 times to 55 times of what the data is. And particularly, you notice data centers, which is always known as a big capacity shipper, is still growing substantially over the next few years. And this can be contributed to, not just demand per se, but also the ability for them to provide more with the introduction of 100 and 400 gig Ethernet into their data centers. So you can see we have a lot to deal with. And you may be asking, why are you developing 2 new speeds in this project? Well, we know how long it takes to do a project. Roughly, as a rule of thumb, is about 5 years from start to finish. So start being when we actually decide to do it, to the very end when the standard gets ratified. And when we looked at this data and we looked at starting in 2020, 2021, you look out 5 years, a 2x growth would not necessarily help the industry at all. And we figured that 1.6 would make more sense to get that going, because it would really build on what we do for 800. I'm going to go into a little bit more detail with that in a second. Okay, so we're really going to be growing Ethernet from 400 to the next speed, which will be 800, and then 1.6. Now, while we're talking about the max speeds, you may have noticed that up front, the project name for DJ is 200, 400, 800, and 1.6, not just 800 and 1.6. And the reason for that is that this project is not just providing a new maximum speed. It's actually going to be providing a new signaling technology, 200 gigabit per second, both electrical and optical, that then can be deployed to the lower speeds, which really wind up in the lower parts of the network. So when you look at this simple network topology that I've got here on the left, you have your servers going into your, we'll call them leaf switches, up into the spine, and then finally to a router and out into the data center interconnects. Okay, and you can see that these next speeds, when we look at it, we've already got 100 gig is becoming very common in the servers, and now that is going up to a next speed, which would be 200 gig. So by providing 200 gigabit per second signaling technology for 800 and 1.6, we can apply that to 200. And you can also do the same thing for 400 gigabit Ethernet as well. Okay, so in addition to all of those different speeds, if you look over in the far right columns, you see that there are different reaches and different mediums that we need to deal with. In some cases, it's copper-based twin axial cables. In other cases, it's multi-mode fiber or single-mode fiber, as well as even DWDM. And what's not shown here is even the actual physical interconnects that are Ethernet-based inside of people's systems. Okay, so there's a lot of different roles where Ethernet is used. And as we create new technologies to support 800 and 1.6, they can then spread everywhere. And this is actually one of the first times where we've taken, I don't look at this as the next speed of Ethernet. I look at this as the next family of Ethernet, which will have a max capacity of 1.6, but we'll go all the way from 200. So we're going to provide the whole ecosystem a speed jump. And this is really important because one of the big trends that you see happening nowadays is that you're going to hear me talk a lot about like 1x, 2x, 4x, 8x. And the reason for that is that's how people are building systems nowadays. So when you have this sort of port hanging off of a box, it may actually require 8 pairs of cables or 8 fibers. And what people will do is they will use them in a multitude of ways. They may use it as a single max port of 1.6. They may use it as 2 ports of 800. They might use it as 4 ports of 400 or 8 ports of 200. It's all up to them and their application. And this is applicable to all the parallel media that we do. So as well as parallel interfaces. So you can apply this to copper cabling, multi-mode fiber, single mode fiber. And by giving the user that sort of power, it really empowers a whole new level of architectural flexibility that prior speed jumps split it out over multiple years and projects. We're consolidating all this because we'll have a building block that we can then basically just say, oh, this is 4 lanes of 200 or 8 lanes of 200, okay? As well as now, these universal ports, you can plug in something that does copper. You can plug in something that does multi-mode fiber or single mode fiber. So it's really incredible flexibility. Now, I was just talking about the whole lane approach, and this is really a better way to think about the Ethernet of today. So basically what has happened is, a lot of times, and my history goes way, way back. So I've been doing speed jumps. I did the first speed jump from 10 gig to 40 and 100. And I remember a question that I was asked at one point was, well, when are you going to do native Ethernet, native 100 gig? And frankly, I didn't know what the person meant at that point. And what they meant was, well, when are you going to do serial 100 gig? And I had to point out to this individual that there's nothing in Ethernet that says it's done serially. There's nothing. There's many examples of parallel interfaces. One of our most successful projects to date was the gigabit Ethernet PHY that you plug your laptops into or your wireless access points. This is based on 4 pair of differential copper, okay? Twisted pair. So we can be parallel. We've done it before and we do it today. And really that is the future of Ethernet because quite frankly, getting to a single lane of any speed is becoming harder and harder and harder. All right, so now what used to be the popular flavors was a serial speed and a 4x lane approach, okay? Serial was seen as the high volume application, so you could use that in the servers where people were, that was kind of the thinking at that point was when we get to serial, it's ready for high volume deployment. And then the 4x was really the common networking approach. That has really changed. And I think it's a reflection of the challenges in introducing these new speeds. And I don't mean Ethernet speeds, I mean the actual signaling speeds. It takes time to develop this stuff. So now what is becoming more common is you are seeing more people adopting the 8-lane approach that was introduced really in the 400 gigabit per second project where we developed 400 gig based on 8 by 50. So you'll notice that I go clear up to 16, and that's because we're already seeing people starting to ask about 16 lanes wide. And, I've even had some parallel optics people talking about 32 lanes wide. Ethernet worries about its broad market potential, and when those flavors really start to show up in mass and as a need, I'm sure that they will eventually expand it. So, as I said, the interface width right now, 1 and 4 is the most popular ones. 8 is now recognized as something that people are doing and will grow. And our signaling rates, well, in this BJ, I'm sorry, I'm getting my projects mixed up. In this DJ project, we are going to be developing stuff 200 gig or greater. All right, so for 200 gig, you can look at here, and a 1 by 200 would give you 200 gig Ethernet. 2 by 200 would give you 400 gig Ethernet. 4 lanes would give you 8, and 8 lanes would give you 1.6. All right. Now, I will say that we do have some objectives, which I'll go in later, that are already looking at serial 800 gig speeds for using coherent signaling. And I've already heard people talking about perhaps doing 4 by 400. So there's different ways to approach the different problems based on the different application needs. And this is a nice, simple way to try to get your arms around the whole totality of the different solutions that we deal with. So now, as we move beyond 400 gig Ethernet, and we start to look at 800 and 1.6, there is broad recognition, and this has evolved over the past couple of years as we've been working on this, is that we've made very rapid progress on the parts of the project that leverage existing 100 gigabit per second signaling technologies that have already been standardized. So there's signaling across copper traces, there's signaling across twin axial cable, there's signaling across multi-mode fiber, single mode fiber, all based on 100 gig a second. So in that case, as I said, we're just changing the number of lanes from 4 lanes to 8 lanes, 8 by 100. So the 802.3df project is actually going to be developing 800 gig solutions based on 100 gig signaling technology, and we're going to be adding to the 400 gig family with some of this 100 gig per lane technology as well. The 802.3dj project is going to be developing copper and optical based PMDs using 200 gig or greater signaling. And really, when I say greater signaling, right now it is 200 gig signaling for solutions up to 10 kilometers, and there are serial lane solutions, 800 gig lane solutions being proposed for 10 and 40 kilometers. And we'll go over that in a second. But remember, there's really 2 projects, and one is fast tracking because it's leveraging existing technology, while the second one, the DJ project, is actually doing the heavy lifting of developing the technology. All right, so here's the 802.3df project. As you can see, there's really only one member of the 400 gig family that's being expanded on for 100 gig signaling. Now, that is not to say that we're ignoring that. It's just that it already exists. So as we were looking at the new speeds, there was recognition that a parallel fiber solution for 400 gig based on 2 by, I'm sorry, I'm getting my lanes mixed up, based on 4 by 100 would be useful in the market. So, and going for 2 kilometers. So we've added that in there. But now we're adding in for 800 gig, all of these different solutions that are based on 8 lanes of 100 gig. So 8 differential pairs for our electrical interfaces, 8 pairs across backplane, and I mean in each direction. So 8 differential pairs to do backplane solution, 8 pairs to do copper cables, 8 pairs of fibers for multi-mode 50 and 100 meters, as well as single mode fiber for 500 and 2 kilometers. And as I said, we are just using existing technology. The 802.3bs project developed 500 meter single mode optics based on 100 gig signaling. The CK project, OWIs, backplanes, and copper cables. The CU project did the 2 kilometer SMF optics, and the DB project did the multi-mode fiber optics. So you can see there's a wealth of tools, tools in our toolbox for us to use to rapidly make progress on this standard. Now, the DJ project, well, you can see that has a lot of objectives as well. So, but what I want you to take away from it is the different rates. So 200, 400, 800, and 1.6, like we talked about before. And it really, most of the solutions, when you look up to the 2 kilometers, is 1 lane, 2 lanes, 4 lanes, 8 lanes, and you multiply that by 200, and that gives you the Ethernet rate that you're attacking. All right. The one interesting thing is that we do have one thing that we're developing based on 100 gig signaling for 1.6 terabit, and that is actually the electrical interface. And the whole reason why we're doing that is to address test equipment, because we're going to want to have 1.6 terabit test equipment available, and we'll need it available before actually 200 gig is available, right? And that way people can start testing it. So we are doing our electrical interfaces for 16 lanes wide. When we go out to 10 kilometers, we do have a solution that will do 4 lambdas over 1 pair of fiber. This is referred to as the LR4. But we also are going to be doing a serial approach. And then at 40 kilometers, we're going to be doing 1 pair over there as well. And IMDD optics are being considered as well as coherent. At this point, while I've said they're being considered, the reality is that the baselines that we've seen are really only coming in as coherent for the 40 kilometers. So, probably a good point for me to touch on is that this presentation is actually happening while these decisions are being made. So this is really a work in progress. So you're kind of getting the latest snapshot of it. So as of right now, I have to be unbiased, right? So what I can say is that while the objective can support either could be resolved or solved with either IMDD or coherent, the reality is that the approaches that we're seeing are only coming in that are coherent. And that would be 1 lane of 800 gig to go 40 kilometers. All right, so let's talk about the actual DJ project, and I'll try to give you an update on where we're at this point. Before I jump into the project, though, it's really important that we take a step back and say what's happening right now in today's world of Ethernet. And there's a lot of different trends that are going on here. I've already touched on the fact that bandwidth requirements are continuing to grow. And I probably should say grow rapidly. So there is a real demand to get these solutions out as quickly as possible. So it really, it's a great driver. A friend of mine used to say that we do our best work when the market is screaming, and the market is looking to get these higher speed solutions. So yeah, we're working right now. There's also been a lot of things that are happening in the world of Ethernet that we see impacting our choices. So forward error correction, FEC, is becoming more acceptable. BI-8 electrical and optical interfaces, which I've already touched on, they're becoming more acceptable. And we already have developed a project, the 802.3 CT project, that does 100 gigabit per second Ethernet over multiple lambdas for coherent-based for DWDM systems. So we've got these things that are happening. We also have new packaging concepts that are happening, and I'll touch a little bit more on that later on, but co-packaged optics, near-packaged optics, cable backplanes, flyover cables, other things. And flyover cables is really like inbox cables. We have to worry about all of these different packaging concepts and address those which people come in, and we are a contribution-driven organization. So as people bring in their ideas for using these different things, it factors into our thinking. I think the other thing that is recognized was that the actual development of 100 gig signaling wasn't easy. It took a lot of work. A lot of trade-offs were done. And, you hear a lot of people say, there really wasn't much margin left and we had to deal with that. Well, with that thinking in place already and that experience, you can imagine that 200 gig is requiring us to think outside the box. So it adds in more things for us to be taking into consideration. Packaging schemes is just one. How we do the FEC, that's going to be a key part, which we'll go over in a second. These are all things that are being funneled into our group and processed and decisions made. All right, so as we look at defining 800 gig and 1.6, this simple diagram would be helpful, right? So first we have our MAC, and you're going to be going over, I'm showing, and this is not meant to be inclusive of everything and exclusive to anything. It's just a general diagram, but you can imagine you have a MAC chip, and then there's some PCB, and you have optics on their module, and the MAC is connecting to the optics via the PCB traces. You've got some type of cabling. It might be copper or multi-mode or single mode, and then you have the same card on the other end. As we start to look at this, a lot of things break out to us. First of all, everybody recognizes that forward error correction will be integral to making this link work. And we're going to really touch on that because that's a key part of where we're at and really affecting a lot of our discussions right now. Second thing is and I think this is one of those ones that sometimes people don't quite get their arms around. We need to enable multi-generational interoperability. And what do I mean by that? Well, remember how I said we're going to be doing 8x100 and 4x200? We want to try to make those work. We want to provide upgrade paths, and we don't want people's systems, when they develop an 800 gig solution, to have to be thrown out when we introduce the new 200 gig based stuff. So we need to make sure that those things work together. Remember, the goal of an Ethernet standard isn't an implementation specification. And what I mean by that is, when we do an Ethernet spec, it doesn't tell you one way that you have to do things. It tells you what you need to meet. And we try to enable as many of these different implementations as possible. This allows innovation, which allows competition, which allows driving costs down. It's been a very successful model for us over the past 50 years. And by the way, today, well, I shouldn't say today, this month is the 50th anniversary of the invention of Ethernet by Mr. Metcalf, Bob Metcalf. So we're all excited to be celebrating 50 years of Ethernet technology. All right, I diverged there for a second. Let's also understand as we're looking at this, but that there are other variables that we'll need to consider besides just how I transport 800 gig from point A to point B. I'm going to need to understand, I've talked about all of these different objectives that we have and all of these different solutions that we're going to be providing. We're going to need to look at those and find out what FEC coding gain we actually need for each of those. Can we make a compromise and come up with a single FEC? Well, we'll leverage it where we can, but chances are there probably will be different FEC codes that are used. We have to worry about power in today's market. That is, in today's world, that is a really key problem. Latency is a big deal. Kind of already touched on that with the copper cables. You have to worry about that because it gets in the way. And there actually are other solutions in the market. So we don't want Ethernet to be not getting further penetration because it has too much latency. And this is, we'll talk about this a little bit further. There are trade-offs that you have to make as you look at these links. And the use of what I call concatenated FEC, which I'll explain in a second, kind of relates everything together. So we don't have separate problems. We have one distinct problem now going from this MAC on the left side all the way over to the MAC on the far side. All right, so from a general architecture overview, all right, this is, I know these building blocks, people sometimes don't get it, but it really is a simple way for us to look at what we're doing. We have the MAC, and then we go to the RS, and what's called the reconciliation sublayer. And then we have the PCS, and that is the physical coding sublayer. And actually, a couple of things to point out here. I've got to fix up this diagram. The physical layer actually goes further up than where it's shown right now. That's just part of it, so I'll update that. It goes all the way up to the MAC. We've got the PMA, and the PMA is essentially where you do the muxing, the demuxing, retiming, and then you have the PMD, and this is what actually drives the different mediums, okay? And the mediums, okay, so the MDI, which I show here, is the connector interface to the medium, and then the medium is the copper cable, the multimode fiber or single mode fiber. So that's a general overview of an Ethernet architecture. We also have what's called an attachment unit interface, all right? And this is really a physical instantiation, i.e. an electrical interface. And we have two types right now that we do. One is to go chip to chip, and one is to go chip to module. And when we start to look at this PMA that interfaces to that electrical interface, that AUI, which is really between the two PMA blocks, we see that we have a bunch of different things that we need to deal with. If you're doing 100 gigabit per second, you have to worry about bit muxing. And when we go to 200 gigabit per second, we'll be doing what's called symbol muxing. And then you worry about your PAM4 encoding. This can be used in the physical layer, the PHY that I was showing before, if that PCS supports it, or to extend what we call the MII, which I'll touch on the next slide. In addition, we allow 2 AUIs per line card, or have been specified in the past. And the reason why we do this is because technology does not happen at the same pace everywhere. You have your ASIC chips, you have your modules. Normally, your higher speed is introduced on the modules first, and then filters back to the ASICs. So you need to provide an interface to allow them to go from perhaps 8 lanes of 100 to 4 lanes of 200. Okay, so we have this in our toolbox. We also then have what we call this MII extender. Okay, and when you look at the MII extender, that really is going from this 800 GMII and extends its presence through a physical instantiation, i.e. electrical interfaces, down to here, where you can see down here right above what's called the PHY. So this allows us to do a couple of things. One, it allows us to attach different PHYs to that extender if you want, so you can have some personality control if you want and change it. It also allows you to cover or extend that presence of how far on the circuit board the MII goes. So rather than being at the MAC, it may be carried over an electrical interface and moved closer to the edge of the board, which can become important for some of the physical layer solutions that we provide, right? The cons of using the extender, obviously, power and latency. So it's one of those things that we go in our toolbox. We may use it or specify it in some ways, but ultimately it will be an implementation choice. All right, now the DJ architecture. I'm going to go into a little bit more detail, but before I do that, I want to touch on the FEC schemes, because that's really been the big point of, I don't want to say contention, but of debate within the group, right? If you think about it, there are 3 types. You can have an end-to-end FEC, which means I apply FEC at one point on the line card and don't apply anything again until I terminate it at the far end. And that's kind of shown by the picture on the left. In the case of segmented, well, you have, I call them FEC zones. And this might be, where you use an extender and then you go back to the MII, at which point that FEC has been terminated to enable the AUI. Then you have a FEC that's applied to the PMD. And then once again, you terminate that, and then you have FEC for the FAR extender. This leverages, obviously, the MII extender. And as I pointed out, it really is an implementer's choice. So even if you have what's called end-to-end FEC, you could have a segmented version of it because you can always add an extender. So, it becomes challenging because you have all of these different terms that you have to deal with. I'm going to point out, though, once again, with the segmented FEC and the use of the extenders, there's increased latency. And some solutions are very latency sensitive. So it's not always an option just because of the performance requirements that are needed for the solution. Now, the third type of FEC that we have to consider is what's called concatenated FEC. And this is where you have an outer FEC that's applied at the beginning, at that far end, like we were talking about before. And rather than terminate it, you apply a secondary FEC, an inner FEC. And there's essentially a multiplied product of the 2 FECs that increase your signaling gain, your coding gain. And we can use that. That has reduced latency and higher gain. Has higher latency compared to lower latency compared to the segmented FEC, and it's got increased FEC gain compared to the end-to-end FEC. So from the DJ perspective, our architecture, actually, any one of these options is being considered, all right, or is being specified. And what's happening is that the people who are proposing different solutions for the different objectives that there are, all have to decide what are they trying to deal with. For example, the parallel single mode fiber that I talked about earlier on that's going 500 meters and 2 kilometers is leveraging what's called a concatenated FEC approach, where there's an outer FEC and an inner FEC. We're trying to work through this for all of the other things. You can imagine how, in the case of the copper cables, that secondary, and that would be a very short reach. Typical for a server switch connection, you have to be latency sensitive. So we're going to try to use end-to-end FEC in that situation. So in addition, the 40 kilometers, or even in the future that does DWDM optics going 80 kilometers, you may use the segmented approach there because you want that super strong FEC to apply to going 80 kilometers. So we have a very flexible architecture that is dependent upon the solution being targeted for each given part of the spec. All right, so the key decisions that we've made to date so far, and as I said, this is a work in progress as I'm giving it to you. We've adopted an overall architecture. We have adopted an RS 544, 514 FEC, Reed-Solomon FEC, for all of our 200 gig per lane AUIs. You can think of this as the quote-unquote outer code FEC. We have decided on using differential PAM4 signaling for our electrical interfaces, and for our DR and FR optics, which is our 500 meter and 2 kilometer solutions, we're using PAM4 signaling, and we're using an interFEC, and that FEC is a 128/120 that's then based on a Hamming code 6860. Okay, so as you can see, there's different things that are happening as we deal with that whole cascade of problems that are in front of us. Now, I'm a big believer that a picture is worth 1,000 words, and this is a really good example of this. So in the case here, we've shown the three different approaches, end-to-end, segmented, and concatenated, to give you an idea of what we're talking about. So you can imagine, first of all, you have the MII, and there could be an extender above it, right up here, and that's across all three of them. We're not showing that because it gets a little complicated with all of these different variants. But in the end-to-end FEC, you have a FEC that's applied during the PCS, and it goes down into the PMA across the electrical interface, and then onto into the PMD, which then drives whatever the medium is. In the case of the segmented FEC, you come out the MII, and in this case, we're using the extender, and you can see this FEC-E in the two boxes that are shown there. So the FEC-E here going in the transmit path would encode it, and then it would be decoded, go across the MII, and then the new FEC targeting the PMD would be applied. And then in the third case, you have, I was saying, the MII, and in the top PCS, you have this outer FEC, and then you go across your OWI, and then an inner FEC is applied at this secondary FEC layer, and then it drives the medium. One thing I'll note here is that this diagram is very general, so we've had to distinguish between them. So you'll notice, for example, I have PCS1, PCS2, and PCS3. And that's done simply to start off at an unbiased position and not make any assumptions. The reality is that we are coming towards consensus on a universal PCS to use for a large number of the different physical layers, and there may be more PCSs that get added in the future, but right now our focus is on one PCS type. Going back once again, I said the FEC scheme that gets employed is dependent upon the physical layer specification being targeted. There may be reuse of FEC codes, there may not be. And the MII, the extenders I talked about before, can extend the physical reach and can actually enable different PHYs to be applied. So that's kind of just a simple way to look at it. And then I touched on this before when I was talking about the different technologies and that are being introduced. And this is kind of working into our electrical interface specification discussions. All right, and you can see that there's different ways to skin the cat, right? So you could have, in terms of getting from this big chip all the way out to this module here, and in this case I'm showing optical solutions. You can have an electrical optical engine in our module. You can imagine using traditional circuit board traces and going through a chip-to-chip interface with some sort of retimer that then goes to a chip-to-module. And that chip-to-chip may or may not be there depending on the implementation. Ideally, it's not there. You can just drive out. That's dependent on the implementation. You may have the case where there's a big chip and this AUI is being carried over an inbox cable. I referred to this as a flyover cable earlier on, going back again to that electrical optical engine in a module. But we're seeing new technologies as well. You have near package optics where the EO engine is on the board around the chip, and you have an AUI that connects to that then goes to an inbox fiber out to the connector, the MDI. Or you also have what's called the co-packaged optics, where you have the optics packaged with the chip technology itself, then connected to an inbox fiber. All right. All of these discussions and all of these different things are focusing in or are being pulled into our discussion on defining an AUI electrical interface. They all have different channel performances. Some of them may be long, some of them may be short. There is a difference between long and short channels. For those of you who are familiar with copper, you know that loss can sometimes be your friend. And sometimes having a low loss channel can then cause multiple reflections, which can cause problems. So we've got very different channel performances that we're trying to take into consideration. And because of those different channel performance requirements, it makes the whole, what's the BER that we can meet? What can we do there? What's the challenge there? And trust me, that's a very lengthy conversation. I've sat through them, as well as, the interconnect characteristics themselves. Remember, we're writing a standard. We're not developing, I should say, let me rephrase this. We're not developing near package optics technology, but what we're trying to do is figure out an AUI that can be used with near package optics technology, which means we have to know what the channel between the chip and that engine is, and make sure that the AUI that we define can actually cover it. All right. So these are all the different challenges. And as we go to 200 gigabit per second signaling, it becomes tougher and tougher. As I just talked about, there's a variety of channels, variety of channel performances. So we're starting to look at using link training for the 200 gig signaling to make this easier for the implementer to actually use. All right. So tying this all together, and this is right now, I would say this is the heart of the challenge that's in front of us. And let me explain what's going on here. So when you look at our project objectives, we have this MAC to MAC BER requirement per our objective of 10 to the minus 13th. Now, I know many of you are going to say, oh, I need better than 10 to the minus 13th. Understood? That's different. That's an implementation choice. From our specification perspective, that's what we have there. That's what we target and build on. I constantly hear we need 10 to the minus 18th or better. And yes, we get that. But now, remember, we've got to divide all this stuff up, and we've got different effects, that inner and outer effects that we have to apply. We have different channels. We have different requirements on those channels, and we've got to play games with all of this, as well as I just touched on, when we look at these AUIs, we've got different implementations, okay? So you can think about it this way. I've got to meet this outer requirement of 10 to the minus 13th, so that sets my max budget. I can divide that then and think about the line cards and the AUIs on that given line card, the BER then of the medium, so really the module to module, and then look at it from the BER on the far AUIs. And I would say this is conceptual at this point. The specific details and budgeting needs to be worked out by the task force. As we look at the line cards, then we have different BER requirements on the chip-to-chip interfaces and chip-to-module interfaces. We got to put all of this together, and make it work. So you can imagine the challenge here, because you have people who are developing line cards, and they want to get as much coding gain from the FEC as they can to apply to the line cards, which could drive down cost or make their implementations of line cards easier. From the optics and the medium in between, well, you got to worry about making sure that can work. And then at the far end, you've got a different vendor with their own set of requirements. So we've got to provide BER requirements for each of these, so that nobody steals from the other person's budget. And that when you put it all together, like true Ethernet, it works, plug and play. It's fun. We're having a lot of debates on this. Okay, so as I said, that whole FEC issue is really taking up the bulk of our time right now, but there is other progress that's being made. First of all, I'm going to say that there is, as I said, this is a very, very big project. This is probably one of the biggest projects. I think it's the biggest project in the last 20 years with all of the different objectives that we're doing. It's big, but we're still looking at adding to it. There are conversations underway to add backplane objectives. And that actually winds up being really important because that kind of sets a max loss target that will get done that will then be rebudgeted and repurposed for the use of doing copper cables. We have had some discussions about active versus passive solutions. The active solutions they've got their own set of challenges. I know a lot of people use them, and there's nothing wrong with them, but from a standards perspective, specifying them has its own set of challenges. And we're trying to figure out, is there a way that we can enable that market better than what we have in the past? So that's kind of the discussion of where we are. Okay, then for the 800 gig 4 lambda operation, this is referred to as 800 G-base LR4. We do have an initial baseline that has been submitted. There is anticipation, I'll say, that the FEC scheme that was being used for DR and FR optics, that concatenated FEC scheme that I talked about, will also be leveraged then for the LR optics. And they're also actually looking at refining the channel specification. Not changing the fiber specifications, but changing the channel specification based on those fiber specifications. So some interesting work there. Now, as I look at the 10 kilometers and 40 kilometers, we have two baselines that have been submitted. Interestingly enough, one uses a concatenated FEC scheme and the second one uses a segmented FEC scheme. Both of these baselines are based on a DP16 QAM, which is great. But they're different, so we have to work through that. And we also see now a debate between C-band and O-band, what the optical wavelengths are that we're going to use. So the 10 and 40 kilometers, that's got its own set of challenges as well when we're looking at the coherent approaches. Okay, so going forward, the roadmap beyond 400 is leveraging a bifurcated approach, as I've touched on. For the 802.3df project, using those existing 100 gig signaling technologies that have been standardized over the past 9 years, the anticipated standard approval is June of 2024. All right, so that's next year. That's a little over a year from now. That's how fast we're moving with that. The DJ project, that's taking time. And right now we're in the baseline proposal selection. So that's why I don't have as much to report to you as you may have wished, simply because we're making those decisions as we talk. We're looking at this point of a scheduled standard approval of March 2026. Clearly that's far out. That's 3 years out. So we'll see what happens as we move along. And in the future, as we look at providing an update to the Computer Society audience of this project, we'll update you on that. I think that's probably a good point right now. If you're going to provide any feedback, which I would greatly appreciate, because I've already discussed with Scott doing updates on this, given the program and the interest in it, please let me know what areas are of particular interest to you, and we will try to do more work in those different areas next time. And perhaps we'd have to do multiple presentations to address all of it. But this 200 gig signaling, both electrical and optical, it's going everywhere. It will be the next thing after 100 gig signaling, and it will revolutionize. It will bring us to the next solution of bandwidth families. With all that said, 800 and 1.6 families will expand. There are other things out there that I can envision using, I could do 2x400 for 800. I can do 4x400. I can do DWDM networks. This is just the first project on, DF is the first project on 800. DJ is the second. 1.6 is just getting started. And I'm going to leave you with these two thoughts. One, beyond 1.6, oh, wow, that should be terabit, not gigabit. Well, Scott, I got some little touch-ups I got to do here. Beyond 1.6, it's inevitable. All right. Look at this. This is a chart of the standards and the ratifications versus the bit rates. Look at that trend. You couldn't ask for a better straight line, trend line than that. So 1.6, beyond 1.6 will happen. It's just a matter of time. And probably the biggest thing that that's guided my career is this little saying that I found. The exponential factor. The greatest shortcoming in the human race is our inability to understand the exponential function. That applies to Ethernet in such a way, both in terms of the solutions and in terms of the market growth. So please, always keep that in mind. We keep growing. Okay, so with that, I'm going to just leave you with these two links. This page for further information. You can go to the DF webpage if you want to, or join the Reflector, and the same thing for DJ. If you would like to join meetings, the calendar is listed right there that you can go and look. Please note some meetings do require registration fees, others don't. We do a lot of stuff virtually nowadays, so there's a lot of opportunities for you to jump in and join. And with that, thank you very much.
Thank you, John. That was excellent. There was a lot in there, but I think you did a great job, taking us through, sort of where things were and sort of where these new task forces are going. Do you just want to repeat one more time? And you all can type this into the Q&A box. What the topics, John? Do you just want to repeat the topics you might like, or
Yeah.
presentation options, and then everyone, you can just type that into the Q&A box, and we'll record that so we can plan future webinars based on what you say.
Okay, thank you, Scott. So what I would say is that I think this presentation spent a lot discussing the architecture and the FEC issues. Clearly, there may be some updates regarding the architecture and FEC, so that would be one area. There may be people who are interested in the electrical signaling or the channels that those signals will be driven across. So that would be two other areas. And then the others is the multi-mode and single mode optics. And I guess as well as the coherent solutions for Ethernet. So I think those are general terms that would help us very much. But, if somebody heard something else that I didn't cover, please feel free to add that in as well. And I'll parse it to the best of my ability.
Perfect, thank you. We have looks like a question just came in. Are you looking to any concerns about interface noise safety aspects in operating at these speeds?
So no, we don't do the safety issues. That's something that we point to. Those are local regulations that people who are implementing need to address. In terms of interference noise, I think you're probably talking about susceptibility, and once again, that's an implementation choice. I could worry about noise from a signaling perspective electrically, and obviously that is something that we do need to worry about.
All right, great.
Okay.
Someone asked, is there a link for the?
Yeah, I know what they're talking about.
Yeah.
So
there you go.
Yeah. So in this case, the web page has two unique URLs. So you can see that at the end with DF and DJ. The reflector is actually the same for both. Okay, and that's because we actually started from one project to begin with, and then which was originally the DF project, and then it splintered. So we just kept the one reflector for each project. I should point out that in addition to these reflectors, and you'll find this if you go to it, there are actually reflectors set up for the electrical work, the optical work, and the architecture work. So you really can focus in, if you wish, to the specific reflectors. And once again, those will be one per each topic that spans both task forces.
Great, thanks for clarifying, John. And everyone, you don't need to worry about jotting these down exactly. You'll be sent these links when we get out the slides to you, probably tomorrow. I know John mentioned there's one or two things he might need to clean up, so if you don't get them tomorrow, probably Friday at the latest. Let's see.
Oh,
I
is the-
don't see any other questions, John. So do you have any final thoughts as we sort of wrap up here? Maybe.
Final thoughts. Big project, lots of work to do. 50-year history behind us, another 50 years in front of us. Um, Look, it's Ethernet, and we continue to keep finding ways to evolve and solve the needs of the industry. Paul Nikolic, who's the chair of 802, has a saying: 802 produces high value, high quality, market relevant specifications. I think that applies to the 802 specifications and clearly to the 802.3 specifications. I'm going to beat my chest on that one, right? There's so much work that goes into these specifications. They're high quality. I can't say enough good things about all the people that work on these efforts to produce the products that we do. And for those of you, like I said, if you want to get involved, come on in. You can go to the web pages, and you will actually have my email address as well. You can reach out to me. I'll be happy to speak to anyone who has any questions about what it takes to get involved.
Excellent.
Scott, I actually do see one question that maybe you can answer. They're asking if there's a certificate, education certificate for this. I don't know that, so I'll leave that one for you.
Yeah, no, I responded to him. No, unfortunately, we don't offer PDH or CEUs for this webinar.
We'll have to fix that.
Thank you, John. You were great as usual with a lot of information, a lot of knowledge, and as I said earlier, there was a lot in here taking us through where we are and where this project is going. I also like to thank everyone for attending today. We do have just a quick programming note. We have 2 more webinars coming up in May. The next one is on May 18th from our Build Your Career webinar series, Applying Emotional Intelligence Daily. And then on May 30th, we have the next webinar from this series, which is our Standards Activities Board series. That is from the Functional Safety Standards Committee. Titled Results and Perspectives. They recently just published an article in Computer Magazine, which is our flagship magazine. I think it was the February issue. All of their latest findings and results. There's a link to the article when you go to register, and there's a link to the article in your confirmation email so you can get familiar about what they're going to talk about. That should be a really fun one. We have all 5 authors on. They're each going to talk about their part, and then we're going to open up to a 5-person panel with Q&A participation from the audience. So that should be a real good one. But again, thank you, John. Thank you for everyone being here today, and have a great rest of your day.
Thank you, everyone. Have a great day.